Let me see. It works on my phone, so it should work on your phone. Yes, all right. Traveling. I like to travel as well. You know my last name, Reiser? In German, the word Reisen, Reisen means travel. And I try to live up to this scrolling Instagram. I have also an Instagram account, but I never use it. Reading books, okay, that seems to be listening to music, of course. Learning new things, practicing karate, watching movies. Yeah, very good. I visited yesterday your gym here in the sports center. It was very nice. Quite a lot of things to do. Yeah. Yeah. And so music is great, of course. Reading books, watching movies. That's what I also do a lot. And one of the things I do and I like to do is I watch all the movies I see and I read all the books I read them in English. So I try to improve my English as much as possible. Because you guys are all pursuing a career in science. And English is the one skill, besides being a good chemist, you really need to master. And I know that India is, of course, very complicated because you have so many languages. You have Hindi, you have your local dialects, and then there's also English in addition. But if you start a job in industry or academics, then English becomes really the one important skill. And you need to master it beyond survival. It's not enough that you go to a restaurant and you say, give me food, right? And then you need to get it to a higher level. You need to write good papers. You need to make a polished presentation. And that is very important. And so I have a Netflix subscription. I have it at home. When I do sports in the evening, I do it in front of a TV and I watch a movie in English, right? And I do this and I also read books and I also listen to music, but I also like to read the words and the text and so on. Sleeping, that's a very good thing in your free time. Playing badminton. I saw this yesterday. You have these beautiful badminton courts in the sports center, right? I was very impressed with this. Okay, so quite a bit of things, and yeah. So let's see how this all relates to chemistry. Let's do some Chinese now. Does anyone know? Can anyone Chinese, Mandarin, anyone learning this? Probably not, right? I didn't learn this either. Does anyone know what this means? This is the Chinese word for matchmaker. That's what they use for matchmaker, right? When two people are supposed to get married and to meet, then very often you have a matchmaker who arranges this. And the Chinese use the word matchmaker also for catalyst, because that is exactly what a catalyst is doing. The catalyst is arranging the reaction partners. It makes it easier for them to meet, easier for them to make a connection, but the catalyst, the matchmaker itself, is of course not participating in the reaction, in the product in the end, which brings the two people together. So I think the Chinese were very clever to associate the word catalyst with the word matchmaker. So it's the exact same thing in the Chinese language. Okay, so here's now a question with multiple choice. So what can a catalyst do? And I can give you four answers here. And you can see that you can now answer probably most of the time the questions which are being asked is you can answer more than once. You can give multiple answers, and we can see what it can do. All right, so you like all the answers which you give here. So top answer here is accelerated reaction. That's of course indeed true. That is what a catalyst, a matchmaker, can do. He brings reaction partners together so that they can react faster, and also even to make it possible, so make the reaction possible. Catalysts in theory could live forever. In practice, it does not, right? In practice, we all know that there's catalyst poisoning, and so we will have to talk about turnover numbers and turnover rates, which is a very crucial parameter to evaluate a catalyst. The one thing a catalyst cannot do is the one thing you said here, change the thermodynamic equilibrium between starting materials and products. That is something, I think I have the graphics here on the next one. This is something the catalyst cannot do. The catalyst cannot change the energy where the reactants are to the product. This is not possible. We will have a lecture where I will introduce to you the concept of uphill catalysis, where by a catalyst we are able to convert reactants to products which are higher in energy. But again, the catalyst itself cannot change where the energy of the reactants is and where the energy of the products is. And so typically we look always at reactions which are thermodynamically favored. So we go from high energy reactants to lower energy products, and that has always an activation barrier, and the catalysis can lower this barrier, right? So this is what the catalyst can do. It goes by a different pathway, and it can lower the barrier. This is a very simple picture. Very often it's like this, that in the catalyzed reaction you go through multiple intermediates, and we will look at some catalyzed processes as well. But overall, the total barrier is reduced to the uncatalyzed reaction. So that is the function really the catalyst can do. Okay, so then I already mentioned a few things already on this. So what are some of the parameters you need to evaluate how effective a catalyst is? Right, have any ideas on temperature? Okay, temperature and pH. So with temperature, you probably mean at what temperature a reaction is possible then. If you maybe have an uncatalyzed reaction which needs 200 degrees, and now you suddenly have a reaction, the catalyzed process, and there the reaction is probably possible at room temperature. But that is the function of the catalyst. This is not the effectiveness of a catalyst, right? Yes, if you can lower the temperature, but that's the catalytic process, the reaction itself. But it does not tell you so much about the performance, right? Product percentage, of course. How much product can I form? Turnout rate. I think what you mean is the turnover rate. Turnover frequency, I cannot write on this right now, but I can write on the next page. So these are probably very important things. So solvent atom economy, but again, the atom economy is the reaction. The catalyst cannot change really something on the atom economy. It can just make it faster and can make it easier. Let me give you here a few parameters which you might want to consider. So first of all, you might want to consider the type of the catalyst. And that is very often connected with how abundant is the catalyst, right? Do we use a precious metal like platinum, iridium, gold? How precious is gold? You might want to think about this. Or can we use iron? Or can we use no metal at all? Can we use an organocatalyst? One of the other thing is, can we recycle it efficiently? Because we might want to use a very, very precious catalyst, like iridium or so, but if we can recycle it efficiently, then it might be very acceptable. And that is something one must really praise industry. Industry is extremely efficient in these type of recycling processes. And so things which we would not consider to be very green, because iridium is very scarce on our planet, it is still, if you can use it over and over and over again, it becomes still very acceptable. And this, of course, is connected to the turnover rate. How many cycles can a catalyst do? And then when you recycle it, can it do so many cycles again, right? So the turnover rate is very important. And then also the turnover frequency. How fast is it? And I will show you examples, Nobel Prize winning examples, which probably are not practical, because the turnover frequency, how fast the catalyst, how many cycles per hour or per day sometimes it is doing, right? Toxicity is a very important issue, because very often when you make a product, you have contaminations of your catalyst, and it depends for what you're using the product. But for example, if it's pharmaceuticals, if it's a drug, the allowed concentration of a catalyst which can remain in the product, and we have a tutorial for this today, we have one question for this later in the tutorial this afternoon, has to be minimal, very, very minimal. And so that's very often very hard to remove. So that's also something to be taken into account very, very much. How toxic is my catalyst? And there is, for example, the thing, if you use any organotin compound for a synthesis towards a pharmaceutical compound, you cannot do it, because you're never able, even if you do chromatography and all these things, you're never able to remove it to a sufficient, to a low enough quantity that you can leave it in a drug. So organotin compounds are considered to be very toxic. And so when you develop a reaction, a sequence to a drug in the lab, and there's at any time you have tin in there, if you would go then to industry and say, hey, why don't you make my drug with my process, they would immediately say, it doesn't matter how efficient and how great it is, we need to get rid of the tin step in here. And so that's very important. So turnover rates, frequency, that's also important. Selectivity, of course, right? How selective? Very often I can form different products. Reaction temperature, that's what you have said. How low can I go down? And one issue which is also very important is sensitivity, of course. How robust is my catalyst? Can I tolerate air? Can I tolerate moisture? And that is something we learned over the years when I started chemistry. I did a lot of palladium type cross couplings, and we thought that oxygen is very harmful, water is very harmful. We also thought that the reaction temperature needs to be low. So with reaction temperature, you can I lower it? But also the question, can I run the reaction still at high temperature to make it very, very fast? Is my catalyst accepting this? And that is one thing I tried in my PhD. I tried to do the palladium cross couplings not more than 40 degrees. Room temperature would have been even better, right? And no oxygen, occlusion of water. If I would have been more daring, I could have done many of these reactions at 100 degrees, 120 degrees, no consideration for oxygen. The palladium catalyst would have been okay with this. So robustness is very, very important. Then if you have a catalytic process, it's also important that what type of reaction the catalyst is catalyzing. And there, of course, we want to have starting materials which are readily available. If you have a catalyst which can only catalyze a very specialized reaction with difficult to obtain starting materials, this might not be worthwhile so much, right? We talked a lot about waste already, so little waste we want to have. We would like to have ideally no additives. we would like to have benign solvents, right? Which solvents is it tolerating? And again, many catalysts tolerate water. You can even run many catalysis reactions in water. But also, the question how green is water as a solvent is questionable if it comes to getting rid of it, right? And then we of course wonder how pure is the product, are there byproducts forming, how easy is it to isolate? So lots of things to consider here. Okay, general types of catalysts. What do you know? Just general, not too specific. Nickel zinc, this is already very specific. I would say nickel zinc I would put into metal catalysis, right? Okay, very good. Okay, there are some of you making the distinction homogeneous or heterogeneous catalysis. Very, very important distinction because at a heterogeneous catalyst, that is something industry likes specifically because it can be easily filtered. I showed you this reaction, this synthesis of the iodine from BASF. They were using 500 degrees on the silver oxide catalyst. That's heterogeneous, which you can heat indefinitely, and it's not going into solution, so there's no separation problem, right? So homogeneous, heterogeneous, then indeed metal catalyst. So you say palladium, and so I will all put this into metal. You say photocatalyst. That can be metal or organocatalyst. Some of you also said organocatalyst. It's already gone here. Biocatalyst, very, very important. Very, very important. Again, there are companies who are really experts in using biocatalyst in the BASF, for example. Again, they have a huge unit for biocatalysis. And it comes to the point that you should consider a biocatalyst like an enzyme, like a normal reagent or catalyst. And so it comes to this. Okay, so you guys have very, very good idea. Ziegler-Natta catalyst, interesting. You guys bring up very important catalysts. I show you the Ziegler-Natta catalysis in a moment, because indeed this is one of the big processes which is being used in catalysis if we think about what type of catalyst and what catalytic processes industry is actually using. So you have a great idea on all of these things. And so if I just go very general, I would have ordered it and say there are metal catalysts, and this can be Lewis acids or can be redox active catalysts. And the nice thing this is you can tune such metal catalysts by ligands, and you need to consider that you might contaminate your product with the metal, right? That's the one thing to consider. Organocatalyst, a Nobel Prize was given to Benjamin List and David McMillan. I talk about this a little bit more. This can be bronzite acids and bases, and it can be carbene catalysts and quite a number of other things these days. It's metal free, so there's no metal contamination product. And again, you can tune them by putting on functional groups. Enzymes, you put up, and probably more modern or more recent, which became very much in the focus is like light photocatalyst, but also the light itself as a catalyst, and also electrons, right? The electron can be a catalyst in electrocatalysis. You can argue, is this really a catalyst or should I put it here? But these are, we have the term now electrocatalysis, photocatalysis, so that certainly plays a role. Name the 3 most abundant transition metals for me. If you now talk a little bit about metal catalysis. Okay. Iron, copper, zinc, cobalt, iron. Okay. Rhodium, palladium. I must disappoint you. Rhodium and palladium is very, very scarce. Rhodium belongs to the 3. I shouldn't take this away because I think the question is coming. Which one are the least abundant? Okay, Titanium, very good one, very good choice. So you have all a good idea. Many of you were saying iron. Iron is indeed the most abundant one. The second most abundant one, nobody. Oh, no. I'm getting ahead of myself. Manganese, indeed. That is the second most abundant one. And then probably it's not nickel, cobalt, copper, and so on. It's probably all in the same region. We have enough of this. We have a lot of this on Earth, but probably it's titanium which comes next. And I think I have a picture of this. But so if we say iron or manganese, now here's my next question. We have a lot of this, but can you name a catalytic process? Can you name a reaction these metals can catalyze? Okay, the Haber process. That's very good. Question is the Haber-Bosch process catalytic in iron? You're absolutely right. This is being done. The Ziegler-Natta process, which is titanium and aluminum, or zirconium and aluminum. So that's pretty good. But I would give it to you that probably the one thing which is closest is if you want to use iron, right? If you want to use iron, then it's probably Haber-Bosch process is a good thing. Hydroformylation, we talked about this earlier, as rhodium or cobalt. That's not, I'm not really aware, although we will go through an advertisement, because my group, we have developed a formal hydroformylation with iron. We will talk about this. The Wacker process, interesting. Now you start, oh God, I need to go to the next question, because now you start putting up processes I don't know. So the Wacker process is palladium. Oswald process, I'm not sure actually, and Cativa process I thought is iridium or so. I'm not sure. So you guys see that you have a lot of ideas about catalyzed reaction, but if you think closely about iron, very little iron catalyzes. Iron is doing stoichiometric. We talked about nitrobenzene to aniline. That can be done by iron, but that is stoichiometric. One molecule of nitrobenzene needs 9 molecules of iron. And very often, you see, that's very often what we say. We say it's catalyzed by iron, and this catalyzed by iron, we might want to say it's being made possible by iron, but it's not really catalysis, right? And so if we think about Earth abundant metals in the third row, there are still very little reactions which can be catalyzed, and most of the reactions are in the regime nickel, copper, cobalt. That is all there. But iron, manganese, the metals we really have a lot, there is, funny enough, not too much real catalysis around. That might be something for you when you start doing PhD, or you already do PhD, or later on working in industry. I think that is something which is would be very important to develop. Can we do a Heck reaction, which we do with palladium? Can we find a way to do it with iron? That would make a very, very big impact, right? And so this is what we have said. So these 3 abundant, let me skip about this, because I already said it's rhodium. And there you probably could say a lot of reactions which are catalyzed by this, rhodium, iridium. Here is the thing. So iron, manganese, and titanium. These are the 3 metals we have really a lot, and we are using. Of course, you all know what we are using iron for. We are using iron to build skyscrapers, right? So it's used for buildings and so on. It's not that we don't know what to do with iron. Titanium. What are we using for titanium? Paint, for example, it's white paint, it's titanium dioxide, right? So again, we use this a lot, but we use it a lot less for chemistry. Manganese is probably one of the things which might become important as a substitute for the Haber-Bosch process to activate nitrogen. We know that enzymes can activate, manganese-based enzymes can activate nitrogen to make ammonia, right? But overall, we do not know so many catalyzed reactions. You know many stoichiometric ones. You know oxidations with potassium permanganate, for example. But that's all stoichiometric. That's not catalytic. And then the chemistry we really know very well in catalysis are the precious metals, like palladium. You see here, palladium, rhodium, ruthenium. But you see, taking into account, this is a logarithmic scale. So if I go here from iron, which is like 10 to the power of 4 ppm abundancy, then rhodium, we are suddenly 10 to the minus 5 or so. Iridium, which everybody likes now in photocatalysis, is the scarcest element we have on the planet. There are only 6,000 tons of iridium. That sounds still a lot, right? There are only 6,000 tons of iridium on the planet. And the fact is, it was very long, it was very inexpensive because nobody knew what to do with this and so on. It was much less expensive. Look at gold. Gold is about 1,000 times more abundant than iridium. But gold was for the longest time because we make jewelry out of this. It was much more expensive. But now people realize that iridium, because we are using it not only for photocatalysis, we are using it for the lamps, for LEDs, very little fortunately, but it is a very scarce compound. So iridium, rhodium, also osmium. One of the reasons, probably the Sharpless dihydroxylation, for which he got a Nobel Prize, never made its way into industry, was that you needed around 0.5 mole percent catalyst. So the osmium would make 200 turnovers, but you can see how scarce it is. And if you want to make a ton, even just a ton, we are not talking about millions of them, if you just want to make a ton by an osmium catalyzed process, and if it needs 0.5 mole percent of the catalyst, this means probably you need 500 grams of osmium, right? And so that was very prohibitive, and as great as that development is, as little it was used. Some of you said, when we talked about what type of reactions you can do, somebody said Wilkinson catalyst, right? That is a very important. This was a rhodium catalyst for hydrogenation. This indeed made it into industry because there you can make 1 million of turnover, and then using rhodium, and then especially if you're able to recycle this, was acceptable. And so that is an example which made it into industry, but also Wilkinson got the Nobel Prize for developing such compounds and showing that such complexes can be used as catalysts, right? And we have seen other Nobel Prizes. We have seen the Nobel Prizes for the palladium type cross-coupling, because that's also very broadly applied in industry. And you can see that palladium is, from all the precious metals, is probably much better than rhodium or iridium, but you can see palladium and platinum is relatively similar, and gold is actually more abundant than palladium. So it's often very interesting when we use palladium, and for many cross couplings we use like 10 mole percent of palladium. That is a lot, and that is a lot of a very precious, very precious. Very precious metal. Just note here also, we hear so much about rare earth elements, right? We heard this to make batteries and lots of this. It's called rare earths, but they're not really that rare. So you can see here cerium is as abundant or very close to copper, nickel, cobalt, and so they are relatively abundant. The problem is, in a battery, you need them almost stoichiometric. So that again is always the question. Okay, so here we have some again. So the top three, I should probably put this up. Is the third one is actually not titanium. The third one is actually chromium, And so again, not so much catalysis. We use chromium for oxidation, so Jones oxidation. It's all stoichiometric, right? So we have a certain disconnect about metals we have abundant, but then about metals we can use for catalysis. So the least abundant ones, like here, rhodium, ruthenium, iridium, I made this table just for photocatalysis, because these are typically metals we use now also in photocatalysis. And so we have a certain disconnect about abundancy and efficiency as a catalyst. Okay, so some of you said the Ziegler-Natta polymerization, and that is indeed a great process, and I would like to emphasize what catalysts can do and how far we are away in many of these issues. So the Ziegler-Natta polymerization started in the 60s. It got the Nobel Prize in 1963, and it made so much money that in Germany, the Max Planck Institutes, especially the one in Mülheim, Kohleforschung, could be funded by this. So Ziegler did not use the money which was generated from the patents for these polymerizations. He did not use it for himself. He used it for science. He gave it back and made research foundations. Natta, Italian, he was more like having a great life, and actually that's what the Ziegler and Natta thought about this, because Ziegler said everything should go back to science, and Natta said some should come to me, right, for these things. So what they developed is they developed the polymerization of alkenes in a very spectacular way. So this is here the most easiest one probably to make polyethylene. And what they were using is they're using a combination of here titanium and aluminum and triethyl aluminum. And what it does is it made very, very high molecular weights once, but you will see that this can go up much, much higher. And the interesting thing was you didn't need pressure any longer. This would do it at ambient atmosphere and at relatively low temperature. And the mechanism for this is pretty well known, that the titanium, you form a titanium alkyl species, and then an alkene is coordinating to this, and then the alkyl group which you have on the titanium moves to the alkene, and then the alkene carbon moves to the titanium again. So you see, you're just extending this. You go, here you have a shorter one, here you have the longer one, now the next alkene can come, and this repeats over and over. And so this is how it started, but then it became, and then the second generation was not using titanium and aluminum. This was using zirconium. It was using the zirconium bis-cyclopentadienyl complexes. And again, from the mechanistic point of view, it's the same idea. You have an alkyl group already. This is the growing alkyl chain on your zirconium. You coordinate the alkene to this. And then the methyl group is migrating to the alkyl chain, and the carbon of the second carbon of the alkene is coordinating back to the zirconium. And you see, you have this type, and then the next alkene can come. It coordinates, and then you go and go and go on this. And in order to make this, and to make this more effective, in order to make this pre-catalyst, you use this zirconium 4 compounds, so it's 2 cyclopentadienyl and 2 chlorines, and then you added something which is called methyl aluminium oxide, MiO. This is essentially methyl aluminium with a methyl group. This is exchanging the chlorides for the methyl group. This is your starting catalyst, and then the reaction goes. And look at this. 1 gram of catalyst makes you 40,000 kilograms of polymer. That is so spectacular if you look at this, right? This is essentially, we're not taking exactly in the turnover numbers in case, but this is the type of turnovers this is making. This is, so 40,000 kilograms is 40 million grams, right? So that is 1 gram to make 40 million turnovers essentially. That is amazing. And look at the amount which is being done. This is done on a 100 million tons scale. That was the number from 2010. And the very interesting thing is it could not only make ethylene to polyethylene, but if you use propylene, then there is I have this on the next one. If you use propylene, then there is a question of stereochemistry coming up, because if you have the propylene molecule, the methyl group, so you polymerize the ethylene unit, but the methyl group here can be in front or in the back if you have the growing chain. And this can be randomly, that is what we call atactic, but that can be all on the same side, that can be isotactic, or it can be alternating, it can be syndiotactic. And the second generation catalysts which you have now, they developed catalysts which are able to make isotactic or syndiotactic compounds, polymers, selectively. And I've shown you just some of the catalysts here. So a lot of that depends on steric. You see they made sterically bulky, not only cyclopentadiene any longer, but they use the individual ligands, and then the chains try to avoid these large groups, and so therefore you build up stereochemistry in the growing chain. And this makes polypropylene almost in a crystalline form and very durable. It gives you very different properties than just if you polymerize in a random way, like with a radical polymerization propylene. And so this way you could make very durable polymers. And so, for example, in your cars, all the light, the insides in the car, this is all polypropylene, but it's all polypropylene coming out of the Ziegler-Natta type processes, and that makes it so hard and so durable. Or if you have these suitcase, if you go traveling, if you have a hard suitcase, nowadays we have a lot of these soft suitcases, this is polycarbonate, but the hard ones, which you can essentially not bend, this is all polypropylene. Okay, so then let's talk about homogeneous catalysts some more. And again, the question is it acceptable now to use precious metal? And here are some hydrogenation catalysts, and we already said that hydrogenation is probably one of the mostly used catalytic reaction, but it's also being used in an asymmetric way, and there, of course, it becomes very relevant for drug chemistry. And so here, typically, the metals which are being used are ruthenium, iridium, precious metals, which are very, very effective, and you can see here some chiral catalysts, which not only give good EE, but they give spectacular turnovers, 2.4 million here, one development of Noyori. This is the famous transfer catalyst which he used, which has two different ligands. It has a BINAP ligand, a phosphor ligand, and then it has a diamine ligand. And you see here the turnover frequency, not only that it can do a lot of cycles, but the turnover frequency is with 63 per second. So that means it makes about 20,000 cycles. I hope I calculated this correctly. No, it makes 200,000 cycles an hour, right? So 63 times 3,600. So very, very, very efficient. And then the ruthenium catalyst, iridium catalyst, which were later on developed, would push this up even further. So now we are talking, again, we're talking million tons. You see they have more specialized chiral ligands, so the enantioselectivity also went up quite a bit, and so the hydrogenations clearly are very, very efficient, and there you can argue that it is absolutely acceptable to use such a precious metal because it is so effective in its turnover. And I show you, I think it's on the next slide as well, but also in the tutorial today, I would like to discuss with you the synthesis of nicotine. And nicotine is being used as an alkaloid for many applications, and it's being typically produced also on the ton scale. And one of the key steps in order to do this is to do an asymmetric reduction. You see you have a chiral center here. do an asymmetric reduction of the ketone to the chiral alcohol here. And that can be done by such an iridium catalyst. And I think I have it on the next slide. So you see, this is what they do. They use these iridium catalysts. They use this starting material, and once you reduce the carbonyl group to the alcohol, and then if you can deprotect this Bock group and then do a nucleophilic substitution, you can synthesize nicotine in a very fast way. And what they have been able to do with these type of iridium catalysts, which I just shown you on the previous slide, is they can do this with a substrate to catalyst ratio of about 100,000. And so this was done in batch processes. This company produced 40 tons of nicotines, but they always did 500 kilograms at a time. And here you can see what they've been using. They're using 45 milligrams of catalyst to make 1 kilogram of product. That's, again, very good. The one thing I would like to discuss with you in the tutorial this afternoon is this efficient enough that we do not need to worry about leaving the catalyst as a contamination in the product? Is 45 milligrams per kilogram sounds very, very little, right? But we need to take into consideration that if you have a drug, you can only have less than 10 ppm as a metal contamination in your drug. And so that's what we do later on in the tutorial. We should think about the question, is this sufficient or not, right? Heterogeneous catalysts, you put this up and said there are homogeneous catalysts and heterogeneous catalysts. And what are advantages of heterogeneous catalysts? Yeah, recycling, much easier, right? Typically, you just need to filter it. You guys like the recycling very much. Simple separation, yeah. Reuse, okay, so we are all on this. Very often they are also very robust and also active at very high temperatures. We looked at this ionine reaction, 500 degrees silver oxide, right? That is something you cannot do with a homogeneous catalyst. Right, so the thermal stability, very, very, very good. And again, the Haber-Bosch process, one of you likes this here, the Haber-Bosch process runs at 350 degrees. And indeed, that's with a heterogeneous iron oxide system. And so again, this is the robustness is a very good point. Reduced contamination, absolutely, right? And so indeed, if you think about homogeneous catalysts, that is very often, they have very good reactivity, but also that's the one thing nobody said is homogeneous catalysts, I can tune with ligands. So I can do asymmetric reaction, I can control stereoselectivity. I have much harder time to do this with a heterogeneous catalyst, like with silver oxide or so, right? And so typically we can do stereoselective reactions with them. But then if it comes to recovery, then it becomes already a lot more difficult. I don't know if you run reactions sometimes in the lab. If you do a reaction on a catalyzed reaction, then you do chromatographic workup. Your catalyst might be somewhere in the silica, but you never recycle it, right? So if you do this on larger scale, sometimes you can try to precipitate a catalyst. You can try to recover it by electrochemistry. That is something only specified companies can do. But I can tell you that in Germany, we have the company Degussa. And Degussa makes precious metals, rhodium, palladium, and all these things. And not any longer, but 20 years ago or so, they were very, very, very generous to us in universities. We could write to them and we would say, we want 50 grams palladium acetate. and they send it to us. We want 10 grams of rhodium trichloride. They would send it to us for free. They wouldn't charge us. They had one request. They said, when you do the reactions and you do the chromatographic workup, we would like that you take, because the catalyst is on the top of your column, right? Take the silica on this, put it in some kind of a box or bottle or so, and send it, once you have filled this bottle, send it back to us. Because then what the Gusser did is they would put electrochemistry onto this, and the precious metals would get deposited on the electrodes. So they could essentially recover everything. And so their biggest concern was that we would throw it away because we would think it's a silica waste. But they could essentially to 100% recover this. And so that was a pretty good deal for us. So electrochemical deposition is very good, but not everybody can do this. Sometimes you can extract the catalyst. And sometimes also a very interesting concept is you can run a reaction in a biphasic system. And so then if your catalyst is in the one phase, you can leave it in that phase. You have your product in the other phase, and then you can extract it. I show you a few examples to this, right? And then we come from homogeneous to the heterogeneous catalyst, and there we have typically, I need to hurry up a little bit here. And there we have typically very often nanoparticles which are supported on some kind of a matrix. The one thing you probably know best is palladium on charcoal. This is nothing than palladium nanoparticles which are dispersed on your charcoal. So that's a typical heterogeneous catalyst, and we have this in many variants. The rainy nickel, this is nickel on aluminum oxide, ruthenium on aluminum oxide. So a lot of ways to have elemental metal finely dispersed on some kind of a heterogeneous matrix. But here's, for example, an example of something we developed in photocatalysis, where we had a polymer. It was just an alkane. We would have the alkane attached to an iridium catalyst, and so this catalyst was soluble in hexane. But then we ran a reaction where our product was soluble in acetonitrile. And hexane and acetonitrile at room temperature do not mix. They form two layers. You have a hexane layer and you have the acetonitrile layer. But if you heat it to 80 degrees, then they mix. So then you have one phase. And so what we did is we had our iridium catalyst. This had the alkane chain, so that was soluble in hexane, and then we had the reaction, a polar reaction, where our product was in acetonitrile soluble. So we heated this to 90 degrees, we had one phase, we shine light on, we did the reaction, and then we cooled it off, the phases would separate, the catalyst would be in our alkane phase, the product would be in the acetonitrile case, and so we just would have to do this phase separation, and then we could use the alkane phase again for the next photocatalyst reaction. So that is one way when you can use different polarities, different phases, you can do very efficient catalyst recycling. And I have to skip a little bit over this. One other thing which people like to do as a matrix, you have palladium on charcoal. That is very good, but that's really heterogeneous. One thing which also becomes increasingly important are nanoparticles. And so with nanoparticles, you can, they are smaller than what you have on the charcoal. And so they are almost soluble, but they're still heterogeneous in a way. So you have soluble heterogeneous catalysts. You can filter them and you can use them. And in our group, we used a lot of these magnetic nanoparticles, and we were able to attach reagents onto the magnetic particles like a tempo molecule, and then we were able to I just showed this here. Actually, you can buy it from Aldrich. You have an oxidation catalyst like tempo you use for oxidations, but it was attached to a magnetic nanoparticle. So after the reaction, you could just put a magnet to your flask, and then all the magnetic nanoparticles would go to the magnet, and this way you would be able to separate the catalyst off. So I go over this just a little bit quick. So we did this quite a lot. And so we were very happy with this type of immobilization of a catalyst onto a support, right? And so use especially also for chiral ligands, we would then try, because if you can have a homogeneous catalyst, but then you can heterogenize it by putting the homogeneous chiral catalyst to a support, attach it covalently. That's what we did, for example, with the nanoparticles. We were quite happy with this. And then there came out this publication in 2016, and you can see this came in Advanced Synthesis Catalysis. It was labeled very important publication, and it came from Johnson Pharmaceutics, a company in Belgium. And they published a paper, and you can see what it says. Why does industry not use immobilized transition metal complexes as a catalyst? Right? So everything we did the last 5 years or so before this, putting catalysts on nanoparticles and so on. And so here they tell us industry doesn't like it. And there might be a very good reason for this. And I could ask you this. Why that is? What do you think? Why they write that industry would not like to use a technology where you take a homogeneous catalyst, which might be very selective for an asymmetric reaction, and put it onto a support, and then make out of the homogeneous catalyst, make the heterogeneous catalyst out of this. And the metal toxicity. But in fact, usually you can separate it much easier. So the metal toxicity is actually a plus, because you are not contaminating your product so easily, because you filter it off in the end, because you have made your homogeneous catalyst heterogeneous. So I would argue that this is one of the advantages, that you avoid metal contamination, because you should be able to get it off. Cost of catalyst. This, I think, is a very good issue. Okay, so let me see about this. I think the one thing which I would think most is indeed the efficiency. So here, this is what came out of that paper. It needs extra steps to immobilize your catalyst, right? So you need to put it on, you need to functionize it so that you can put it on. And so if you have to do the extra steps, your catalyst must be better, really good in your turnover numbers. Otherwise, these extra steps are simply not justified. Very often through the heterogeneations, in fact, your turnover numbers and frequencies go down. So you're actually making the less efficient catalyst, and very often it's also not as selective as the homogeneous counterpart, and very often they're also not stable, because once you have your homogeneous catalyst and you do a run and then you try to recycle it, it might not be your metal ligand assembly any longer, it might be already nanoparticles. And see here, this is one thing where we experience this ourselves. So we put on such a pincer complex, which is really stable, a palladium complex, on an iron nanoparticle, and then we ran Suzuki reactions, and we ran them at pretty high temperature. We ran them in the microwave at 200 watts, so we had probably 150 degrees here. And then after one cycle, we looked at the catalyst, and you could see it was all nanoparticles. So we had essentially destroyed the metal catalyst and have made metal nanoparticles. And so we could have used palladium on charcoal right away, right? So there's really no big advantage of doing this. And so this is, and see, this is then the variant we came up. We simply immobilized palladium directly on the nanoparticles. So we made essentially palladium on charcoal just in a magnetic version. And this was very, very effective for this. So this is something you need to take into account, and I have some more examples in the handouts where you can compare like a homogeneous catalyst, and then you compare to the various immobilized versions. You see here this ligand got immobilized on silica, and then it got immobilized on polystyrene, and then you can see what typically happens is reaction times go up, I talked with someone in the break about time efficiency, right? And so with a homogeneous catalyst needs 1 hour, and then the heterogeneous catalyst needs 30 hours. That is, again, that's not really acceptable. You see, EE is more or less the same. And then the big advantage is that the separation through filtration, that's of course a big advantage. But you can see you need extra step. You see, you needed to put on a silicon linker on the catalyst in order to bring it onto your matrix. And here they had an amine type matrix to bring it on the polystyrene. So you needed extra steps, and then you made the reaction slower. And that was one disadvantage. And so last idea here, metal-free organocatalysis. And you all know Nobel Prize Benjamin List, David McMillan, and they got it for organocatalyst. This is the famous McMillan catalyst here. And you will have one lecture on concepts in organocatalysis as well, and I'm sure that this will be covered, right? So this is a catalyst which can form an imine with carbonyl compounds, and then it becomes a very electrophilic way, and then it can add to the nucleophile like this indene on this center can attack here, this one. So essentially what you're doing, you need to be careful with this pen, is you see what your catalyst is doing. It forms such an iminium cation, right? And the iminium cation, you see the nitrogen has a plus charge. So this is now a better electrophile than your aldehyde was. And then this aldehyde was adding, so this center gets connected with this center. And this was adding this. And because the catalyst is chiral, it was enantioselective, right? It makes a difference if the addition of this acroline comes from the top or it comes from the bottom. This makes the two enantiomers. And then the reaction is finishing. You see here, once you do the addition of the indole, you see you have I would have so much hope they would let me use my iPad for this. You see, once you have the nucleophile, the indole as a nucleophile attacks, you have a positive charge here, and then if you have the nucleophile over here, then you can bring back the cyclization. And so this is how they made, how the McMillan group made this the cyclization product, right? Beautiful chemistry, fantastic, and was not easily been possible otherwise. And you can see fantastic enantioselectivity, very, very good yield, but look at the turnover rates and turnover frequency. On average, let's take the best case here. Let's take this case here because it's easy to calculate. 24 hours. 24 hours, and it needs 20 mole% of the catalyst. So that means the catalyst is making 5 turnovers in 24 hours. So it makes what? It makes 1 turnover every 5 hours. This is ridiculous, right? That is a very, very lazy catalyst, and this way, such chemistry will, in my opinion, probably never be practical. Because think about the amount of catalyst you need, and think about how long it takes. And I think this is an important issue, which also the McMillan group has addressed very efficiently, and also Ben List these days is addressing very efficiently, to have these great principles, how these catalysts work, but make them more reactive in order to allow a faster reaction. There's another example from the McMillan group, his famous Diels-Alder reactions. Again, fantastic selectivities, fantastic yields, but again, here it's a little better. It's 5 more% of the catalyst. It's 20 turnovers, but you see, if you do 20 turnovers in about 20 hours, that's 1 turnover per hour. That is very, very, very slow. And And the work of Ben List in these days is in order how he makes this faster is that he generates these super Lewis acidic and super Bronsted acid catalysts, right? So if you have pKa values here from weak acids to strong acids, he's now developing these very big catalysts which are very, very strong Bronsted acids, which essentially protonate everything in a very short time. And you see here is, for example, here's an example where he's been able to do a Diels-Alder reaction, and this Diels-Alder reaction would not be possible unless you protonate the carbonyl group in order to lower the LUMO. But usually if you would use a normal acid, if it's not a very strong acid, then the protonation would not be very efficient. But the developments of Ben List have these super strong Bronsted acids, which actually very easily transfer the proton to a carbonyl group. They highly activate these compounds, and then the Diels-Alder reactions become very efficient. Here's still an example which might not be so great, but you see low temperature, but still relatively long reaction times. But he has now, I'm not sure if I have this, he has now, here's a reaction. Somebody earlier mentioned the Aldo reaction. Here's the Mukayama-Aldo reaction, which he can catalyze now. And again, it's the same idea. You have this super acidic Lewis acid that protonates the carbonyl group, makes this center more electrophilic. And then you can see here, he's catalyzing now with 50 to 500 ppm. So 1 ppm is 1 in a million. So the 50th part of a million is catalyzing this reaction. You can see the reaction times is still very long, but if you calculate the turnover numbers, this is pretty spectacular, and also the turnover frequency, considering that you're essentially using very, very low catalyst amounts. Nothing can really compare to enzymes so far, right? If you think about biocatalysts, as also people mentioned, so there are, of course, enzymes, for example, the catalase, which we have in the liver, which is transforming hydrogen peroxide to hydrogen and to water, and essentially is oxidizing everything which should not be in our body. Look at these turnover rates, 40 million turnovers per second. That might tell you what you maybe in your lifetime will accomplish for small molecule catalysts, right? This tells us where it could go, to. The big advantages of these enzymes, biocatalysts, is they have incredible turnover numbers and frequencies. They are very selective. But the problem is that they are also very substrate specific, because evolution, biology over millions of years made this for a certain purpose, right? Get rid of toxic compounds in our liver and therefore decompose hydrogen peroxide, but not to do lots of oxidations of all kinds of alcohols, right? So that's the problem, is the big specificity. Okay, so with this, I think this was again a more general introduction for catalysis. So I think we have earned a lunch. Right, so lunch, very good, and then I hope you still like to come back, and then we talk a little bit more about renewable resources.